Alright, so today we'll be continuing on the discussion of processes and threads. Right. So the project you've been given, that you are working in groups, some people chose the topic, some didn't. So if you didn't, you are put into a group and you are assigned. Right. But what we'll be trying to do with an operating system class is to at least cover some of the weaknesses people have as far as multi-threaded applications or multiprocessor applications. Most of the applications you've been writing up until this point, you always just think of one thread of control. But we'd like you, by the end of this class, to be able to think in multiprocessor mode. To think, okay, I can solve this with 2, 3, 4 threads going on. Right. So, from the previous chapter, where we talked about processes, right, we talked about some benefits of processes. Now, as we move from processes to threads, do not leave the knowledge you had in processes behind. The same concepts are there, except that now they are sharing the same space. Right? So in processes, we talked about some key benefits. That is, you can share information if you can have inter-process communication. Right? So you can share information, you can have better speed up, you can have modularity, you can have convenience. Right? So last time we discussed these four. Are there any questions about what these mean? So if you can have inter-process communication, right, that means that now you can modularize your code. So if you pick, yes I am, right, so you can modularize your code. So for example, if you take, OpenOffice is a good example. In OpenOffice, when you actually start the application, it will ask you, do you want to work on Word? They have something similar to Microsoft Word, something similar to Excel, something similar to PowerPoint. And what they'll do is they'll ask you, okay, which one do you want to work on? But you realize that there's only one main program that's running. And what they do is they create multiple processes and they communicate to get the work done. So unlike having different applications, right, they can actually synchronize them and have them work together so that you can have a better experience. And you can see this in Excel as well, or Word. You can see you can pull something from another application, maybe embed a PowerPoint, embed an audio. So if you can have this inter-process communication, you're able to modularize your code, as opposed to writing one big chunk that has a big loop trying to do multiple things. You can break your code into pieces. Right. So that's what modularity will give you. If they can communicate, then you don't have to put everything into one block. You can split it up. Like the date client server in the book. Like the date is separate, the client is separate. But if processes that can happen, then you can split it into multiple pieces. Chrome is another good example that if you look into your task manager, as I said, you find multiple versions of Chrome running. And again, it's the same thing. If the processes can communicate, now they can modularize the tabs to say, oh, every tab is now properly isolated. Right? So that's what modularity will get you. And modularity and convenience do go together. Convenience meaning for the users, it's easier to work if the processes can communicate. So you can maybe be working in Word, you can send the image to another program and so on. It makes it much easier to work in an OS. Right? So building on that, we are discussing threads. Now, when it comes to threads, that means that yes, we could have inter-process communication. But in addition to that, if you can have all of them within the same memory space, sharing information, then you can have responsiveness. Right? So responsiveness means that maybe, so if you are taking something like, sorry, I'm using Chrome again. But Chrome is one of the examples where if something is running and you realize that one tab crashes, for example, it doesn't affect the other tab, right? Or if maybe you are sending email, one tab can be sending email, and even the applications that you have, such as Hangout, these are all just, those are all just Chrome applications, things that are just little browsers that are performing the tasks, right? So they can have and make it seem like it's more responsive. Because now you have multiple threads that are running and handling the task, as opposed to one thread who is running, and until he finishes his job, he won't come and check on what the user input is doing. Right? You will also see this in some video games where you could have different threads handling different aspects of the game. Somebody doing the rendering, somebody doing the audio, somebody doing the video, just so that you can have the responsiveness. That anytime you type, it's not that when you are typing or saying dodge, and then it would say, well, I'm doing video, so I can't handle your dodge command right now, and you are dead, right? So at least if you can have multiple threads that are running, handling the task, then it doesn't have to wait until one thing finishes. You can do 2 or 3 things. I'll show a small demo code doing something similar. Right. You also have economies of scale, right? because you are now sharing the same memory space, you can now be more economical. So realize that if you can share more, then you can become more efficient as far as the resources. So it's more economical if all the threads can share some memory, as opposed to if you do a fork, everybody gets their own memory space. Anytime you fork, you get two different processes. They are going off with their own memory. But with threads, it's well understood that they are going to share the memory space. And that means that you can do much more, especially if you have written a lot of good code, but you just want to, let me find a good example. Let's say you have a database server. The database server, if it's within one process and they are working together, different threads will be doing different queries, but they are all in the same space. But they don't have to make multiple copies of the same code, because they are all in the same space, and they'll just have pointers to the part of the code they are running. One person is running one function, another running a second function, and so on. Right. So I'll show you this as well in a small code that I'll do. And scalability. Scalability is one that we'll talk about in some depth today, just so people can see. People ask me, why should I use threads? If you use threads, you have the potential to scale. Or if you use multiple processes, you have the potential to scale. So you should start thinking of, how can I write code that can scale? So if we start talking about scale, one of the formulae that you should be aware of as any good engineer. Okay, so economy was that one, right? And that for process forking, right? But thread creation shares the same So if you pick Firefox, in Firefox you have multiple tabs, but you will not see more and more processes being created. You will not see more and more. But with Chrome, what it does, anytime it creates, it will use more memory. Of course, some people say Chrome is more, people say it's faster or something, but I just say it's just depending on how they are treating the things. That if the OS is giving so maybe it's a little bit of a cheat. If you know that, the OS is giving every process some time to compute, and Chrome has decided to make more processes, they may seem to be faster. Right. It doesn't mean that absolutely they are faster. It's just that they have picked more processes, so the OS is giving them more runtime. Whilst in Firefox, you say, okay, I have this big process, but there are multiple threads running. So, of course, the disadvantage could be maybe the OS won't give you as much. But so far, I haven't seen too much of a disadvantage. Okay, so you understand the... Okay. All right. So we are going to be talking about Amdahl's law. Right. So there is a formula in the book. It only takes one page. It's actually not even in the main reading. They just did a blue highlight on it. But it's something that any good developer, thinker, engineer should be able to think about, computer scientists included. That is, if you are having, or you are thinking of having things where there's multiple processing, you need to be able to analyze how much better it is once you do the parallelism, or you create the forking, or you create the threads. So this is a formula here. Some people memorize it, but I hope that today at least we'll discuss it and you will understand how you could even come up with this formula by yourself. So there will be some time of the class where I'll ask you, we'll derive it ourselves using pen, paper, and you see maybe if you were born a few dozen years ago, you could have come up with this yourself. It's not a difficult formula. So all it's saying is that if you are going to have speedup is composed of, if you have a piece of code, right, you have to ask yourself how much of the code is serial and how much. So serial means that it's not in parallel. Right. So maybe at the beginning of your code you are setting up some variables, that's not in parallel. But the moment you do a fork, that means I have two things that are running in parallel. So you have to look at your code and ask yourself how much of your code, that's the S, is serial. And it says that the speedup you get is a function of 1 divided by, so S is your, how much is serial? And you add 1 plus S over N. N is the number of cores you have, right? Now, if you just use, okay, let me see if I can make this bigger. Right. Now, if my code is purely serial, right, that means I don't have any parallelism involved. What would be the speedup? How would I do that? I'll just assume that what? I have just one N, that's one processor, and my S would be 1, so I should clone this. Let me do a second one. Oh, I don't know why it's not. Okay, there we go. Speed up if only one processor. Right. So if I have just one processor, that means that everything is in serial, right? If everything is in serial, that means the fraction of my serial, my S there, I'm going to put 1. My S here, I'm going to put 1. And my N here is 1. Can anyone evaluate this for me, please? Right. It will be 1 because at the very least, sorry, this thing is not growing as, let me see if I can reduce this. Small, small, small. Right. So what will happen is 1 minus 1 will be what? 0. That will collapse and there will be 1 over 1. Right. So it means that if I am not doing any parallelism, no threading, no forking, nothing, my speed up is just going to be 1 because comparing my previous performance to my new performance is just 1. Right. Now, if I'm able to design my code and make it that from the very beginning, I have now 2 things that are what? Working. 2 processes. So I'll do the second one. Right. So if I say that my whole code, no part of it is serial, from the beginning, 2 things are working. So I'll just do that one. So 0, 0, N equals what? 2. 2 processes. That means my speed up is what? 2. Which makes sense because, so that means if you actually test this formula against some of the scenarios that you know, that okay, if I have no parallelism, 1 processor, so S is the fraction of serial code. We expect that it's a number between 0 and 1, so it's some number. It won't be more than 1 because 1 means 1 is like 100%. 0 means there's nothing at all. That's 0. But in this case, so speed up if up first was 1. So for 2 processors, I'll be having this case where serial will be 0. That means there's nothing that's shared, right? And 1 minus the serial part will be 0. That will be 1 divided by when N is 2, and that will become 1 over 1 over 2, and it will flip up. So this formula is actually question. How much of your code is serial? So for example, let's say, okay, let's do one example. Let's just do like this, without code. We'll start without code and then we'll branch off into code, right? So this is a very simple problem and I want you to see if you can solve this. It's something that you might have met maybe in SS or GSS. So if it takes 2 days, yeah, this is one of those if greater less than, I've forgotten, people are summarizing something that they use in their minds. You can't see. Right. So it says it takes 2 days to proofread a book if there's 1 reader. How many days will it take if there are 4 readers who proofread? So what will be the answer? We're expecting this to be very fast. Yes, it will be half a day, right? Because for 2 days it's 1 person, but if you are going to have 4 people who are reading, they can split the book into 4 parts, and then they can get it done in half a day. Right. So that means the speed up will be what? When we think of speed up, naturally human beings think of right. Someone said they are lost, or you are fine. Alright, so for human beings, when we think of speed up, let's say you are going to buy a new car. You had an old car, you want to get a new car, and someone says, oh, if you buy this new car, your speed up is going to be maybe 100%. Usually the idea is, if you can do things faster, your speed up should be what? Should be a bigger number. Right? That's for human beings. If I tell you, oh, this thing is 2 times, your idea is that what? It has to be twice as fast. So if I tell you something was 1 minute and I'm going to speed up by 2, that means I expect that what? The time is going to come down. Right? So in general, when people think of speed up, they are going to think of the previous speed and divide by the new speed when they apply whatever technique they are using. Right? So for this one, your speed up previously was, you were using 2 days, and now you're going to be using half a day. So your speed up is what? 4. Is everyone cool? So speed up, this is just English, trying to make sure everyone is on the same page as far as English is concerned. When someone says, oh, there is going to be speed up, oh, I'm going to give you 100% speed up, 2 times speed up. That concept. Anytime people say that your speed up has what? Increased, it means that you're using less time. Right? Or the English is still not there. Is everyone cool? Because is anyone that's not cool? So everyone is cool with speed up. Right. So everyday things we hear from speed up, like if you switch to my ISB, you will get 50 right. People can say something like this. And you understand that means that if I say 50% more speed, you say that, oh, that means 100% of what I had. Now I'm going at 150. Right? Or if someone tells you, be 2 times as fast. That means that if maybe it used to be 1 hour to upload, now you're going to have what? 30 minutes, right? So that means speed up. The normal way you think of speed up, I know you use speed up in everyday language, but what we are trying to do is to get everyone on the same page as to how do we calculate speed up, right? And so speed up is your previous speed divided by your new speed. That should give you your speed up, right? And as I said, it's mentioned in different ways. People say, oh, you get 50% speed up, you'll be 2 times faster, or your old speed was maybe 3 times slower. There are different ways, but it's all about comparing the old speed and the new speed. I hope that everyone is cool. Right. Okay. So let's pick a slightly more interesting, a little bit more interesting, but let's pick it. Right. So let's try this one. So for video production, and this happens to me, currently still happening to me, where you do some recording. The recording process, I can't do anything about it. So I can use one processor, 1 hour to record. But after I record, it will take 1 hour to render if I use just one processor, and about 30 minutes to upload. So I'm saying if you give me an 8-core machine to do this part, to do the rendering part. So for those who are wondering, rendering is when you take, so the recording is the full screen. But in order to to put it online, you have to say, okay, do I want to shrink it down to maybe a smaller file? So you have to ask, how many pixels do I want to use for the video? So if you go to something like YouTube, there will be something like 140p, is it 144p, 360p, 240p, 720p. So there are different pixel densities that they can use. So usually once we finish recording the videos, what we have to do is we have to render the high res, which is the full screen, into something that is a little bit more conducive for upload. Right. So I'm saying that instead of using 1 core to do all 3 parts, I'm going to use an 8-core machine to do the middle part. And my question is, how much time does it take me now, and what is my speed up? So now I've given you a task that has 3 parts: recording, rendering, and uploading. And I'm speeding up the middle part. And my question to you is, how much time is it going to take if I'm going to use an 8-core machine for the middle part? These are nice exam questions. So those of you who are not trying it at all, please make sure that you are fine. Okay, so you had 1 hour, what? 37 minutes. So there were 37 minutes. So you had 3 parts of this process, right? So this process had, sorry, let's see if this thing can quickly, right? So 3 parts, hopefully. If if it is just one core, I have recording. Okay, that part is 1 hour. For my 8 core, it doesn't make any difference. It's still 1 hour. Now, this is something that you realize will happen for some of your projects, some of your designs. There are some things that you can't always make into parallel. Some things are just going to take as much time as they are taking. There's nothing you can do about it, right? So this is what this question is trying to sort of emphasize. The second part is rendering. Right? Previously used to take us 1 hour, right? So if I'm using 8 cores, that means that I have to divide 1 hour by 8, because now I'm speeding it up. So that means, right, or someone could say 60 minutes divided by 8. All right, and the last part is the upload. The upload was taking me 30 minutes. And even with the 8 core, it didn't make any difference, right? Because your upload speed is your upload speed. There's nothing you can do. So the only part that is changing is this part. So the total time previously took me 2 hours, 30 minutes, right? But now it's going to be 1 hour previously, plus 30 minutes, plus the 7 minutes. That means if I want to figure out my speed up is the 2.5 hours divided by, okay, I have to be careful, because I know that someone is going to be tempted during an exam to say divided by 3.7, something like this. Someone will try and do this. This is not correct, right? Because if you think about it, the 30 minutes is half. Right, so please, 625. Okay, so that means that your speed up is, anyone with a calculator? Okay, so that is my speed up. It means that if you give me a processor with that much, I can do a lot. Right. So practically, yes. Previously, I used to have a machine that was proper quad-core with all the glory of. Now this is nice, but it's really not rendering as fast as I want. So it takes me almost as long to record a video as to encode, which just blows the mind, even though it's a newer machine, right? So these are some of the things that you can think of in practice. So it was this 2 hours and 30 minutes. So the speed up was calculated as the previous, right? So that's how I got the 2.5, which is 2 hours and 30 minutes. Okay. And then the new time was 1 hour, 37.5 minutes. And that is 1.625. Remember that 30 minutes is not 0.3 of an hour. It is what? 0.5 of an hour. Right. So please, when we are doing time, watch for the seconds, minutes, days, and so on. I enjoy doing that. So please watch for it. Yeah, so that's a very good point. So he was asking about uploads. So this formula for Amdahl's law, it is not restricted to just coding. It applies to any process. Anything at all that you can speed up. So yes, if someone says, oh, there's 1G, 2G, 3G, 4G, so every single one, you just have to ask yourself, okay, how much better performance am I getting based on the task? Right. So if you're using 3G versus 4G, if everything is fine, we would expect some speed up. And you calculate it the same way, right? Or if, let's say, on campus, instead of just Vodafone, now we are going to get maybe Vodafone, Airtel, Tigo, and we are going to try and bulk upload or something. We expect that we get better performance, right? But then we can sit down and do the analysis. That's what most people can do, right? So you can sit down, analyze the problem, and use Amdahl's law to predict how much speed you should get. Is everyone cool? Once you can predict how much speed you can get, so let's say at the IT department, they sit there, someone says, oh, now we are moving from one ISP to another. You give them the numbers. They'll calculate, and then they are expecting some performance gain. So if they are sitting there and still the things they were doing is not as fast, they will come and ask, okay, what's the issue? Though I should say, in defense of the ISPs, some of the servers don't go as fast as the speed that you have. So just because you bought, 20 megabit per second link, doesn't mean that you're going to get that in practice. It also depends on what the type of server you're connecting to. Can the server even go that fast? Are people cool? Are people understanding that point? If the server you're communicating with isn't even going that fast to begin with, you are not going to get the performance. Same applies to those people who are going off to buy super HD screen, and then you go and buy a very, very cheap deck or player, and you connect it to it, and you're like, oh, now I expect that I'm going to have 3D. I've seen some people doing this, where they hear 3D, 3D movie, and they say, oh, okay, I bought a 3D TV, I go and buy a cheap, CD, put it in, and expect that when I play, I'm going to see 3D. It doesn't work that way. Or if you wear 3D glasses, you take the 3D glasses from the cinema home, you go and sit home and you're like, okay, I want to see 3D. So some of the things, it depends on the performance of the component. Right? So I'm hoping that with this, people now facing any task, even when they're asked to code something, can ask themselves, what speed up do I expect? Right? So if you are doing thesis or something, you can say, oh, this is the theoretical speed up. And then when you actually measure it, you can say this is the actual speed up. And then you can tell if your implementation has certain gaps, or you can explain why things are not as fast as they are. Right. Question then.
With this, does it assume that everything else is going?
Okay, so you have to, for this one, it is just one block of code. Right, one block. But then, if it is going to be threading, that means that even if there are multiple pieces, you will have, so this assumes a lot of things are constant. It just assumes that, okay, all the speed, so the S is the serial part. So you look at your code and you ask yourself, the part that is not multi-threaded, how much code is it? How many lines of code is it? The part that is multi-threaded, how many lines of code is it? And for the lines of code, sometimes people just use, those who do software engineering, sometimes you just use the approximation of each line of code represents some fraction of time. But sometimes different instructions represent different complexity. For example, addition will be much faster than division. Right? So sometimes people will sit down, look at the code and try and estimate, okay, this division, how long should it take? So they'll try and time everything. And using that, they can come up with how much is serial, right? And if you know the serial, you know the parallel. You can either find the parallel, the fraction, and determine the serial determine the parallel. And ask yourself, how many cores or how many threads am I creating? And try and estimate how much speed up should I get. Okay. So the difficulty with multi-threaded applications is, first of all, you have to decide how you are going to split up the task. So for your projects that you are working on, somehow, for most of you, it's just one-to-one, where one thing controls another. So it's not a big deal, right? But for any larger project where you are going to be controlling more and more resources or more and more workers, you have to ask yourself, how am I going to split the task into pieces? Right? For most of you, as I said, you don't have to deal with this. But sometimes you have to ask yourself, can I split this thing into multiple pieces that can run in parallel? And then, sorry, I shall put balancing last. The text has to put balancing in the same position. Right? Sorry, I'll put it here, last but one. Because usually in practice, that's how I do it. So I ask myself, can I split the task into pieces? The next task is, can I take the data, can I split that into pieces? If you can split the data, then that means that there are some things that are independent. Sometimes you can't split data into pieces because things are dependent on each other. Right? Let's say you are calculating Fibonacci series. Fibonacci, one value depends on the other, depends on the other, depends on the other. In that case, you can't split it up and say, oh, you go and calculate from 100 and I'll calculate the first 199. Because what? The things depend on each other. Right? So if the things are dependent on each other, you can't always split. But for some things, they can be split, such as the proofreading one. It can be split. Or even good ones from YouTube. YouTube, when you upload videos, sometimes they can add the subtitles. Right? To add subtitles, the subtitles of the first 5 minutes has nothing to do with the subtitles of the second 5 minutes. So they can break the video into pieces and then process it in parallel. Right? Or if you are doing video rendering, same thing. There are some also online who are going to be searching searching different blocks of code, let's say YouTube feeds and so on, searching for certain words, you don't have to search for the first one before you search for the second. Different people can be searching different feeds. You can do it in parallel, right? So data, you have to ask yourself, can my data be broken into multiple pieces? If it's independent, most likely you can do so, right? So splitting and dependency are together. This one is the trickiest one of all, the balancing. After you split the work and you split your data, how do you make sure that all the cores on your machine are being used at about the same rate, right? It's very sad if you split up your data and you realize that one of your cores is 100% overflowing, still creaking, and your other other three. So if you have quad core, 3 cores are almost free, 1 core is very busy. That means that you are not balancing your work properly. Are people understanding that point? If you have multiple cores, ideally, so let me see how my cores are doing. So, task manager, come on. The OS does provide, oh, there it is. View. Okay, I always get lost. Okay, I think one of these should be the core, sorry. Okay, it's here. Okay, so these are 4 cores that are running, and so far it seems to be doing a relatively good job. So comparing the 4 charts, it seems to be balancing them out. But so this is 1 core, 2nd core, 3rd core, 4th core. If just one of the cores was very high, then I would say that this is not properly balanced. Right? That means that one person is being given too much work. Right? And I know that sometimes someone will say, oh, why? It doesn't really matter if one person is getting too much work. But in practice, if you have overloading of certain resources, so if on your PC, for example, one of your cores is going very high, it means that the temperature of the whole machine will be much higher. And so there will be sort of consequences, such as cooling costs or even network costs. Even if you pick something like, if you are doing an application and I say, okay, we are all going to go and get 1 megabyte speeds, everybody's going to get it. And I can say, oh, for the applications that we are running, we never go above 1 megabyte. It will actually have some consequence to the cost. Because usually if you go to an ISP, the more resource you want to use per second. So if you say, oh, I want to use maybe 100 megabits per second, the cost, it's just so high comparing one package to the next package. So sometimes you want to, as much as possible, get something that would even out, spread out the work so that everything is done with low resources all across, spread evenly, than to just buy one really big machine that does a lot of processing. Right. In practice, one of the companies that did this and why they seem to have dominated for a while was Google. So Google, in creating their web server or their web search, whatever they were working with, they decided to go not with very high-end components, but go with slightly cheaper components that they've networked together. So that means they don't have to go and buy the most expensive, fastest multi-core processor, biggest memory. All they will do is get many cheap machines, network them together, and see if they can get the same performance based on the cheap components that someone gets for the very high-end machine. Right? And once they did that, they were able to scale, and they keep scaling. Even up to today, they keep scaling. So I'm sure now they have more money to buy the most expensive machines. But at the time, doing that enabled them to be competitive. Because they don't have to go and buy expensive machines. They can go and buy slightly cheaper components, put them together, and have the same performance. Right? So are people understanding the point of balancing? If they don't balance, they don't balance, then it means they have to get bigger and bigger, more and more expensive components to do the same work. Right. So back. Right. So 2 types of parallelism, which was hinted at when we talked about how or what are the challenges. Right. So one type of parallelism we talk about. Okay, so after you make the thread, so balancing means that the work that is being done has to be split up such that they are all kept busy at about the same rate. So, for example, let's say I am doing, video. Sorry, I seem to keep saying video processing because I keep doing that a lot. But let's say, okay, let's pick another like health. Right? Let's say I have a program that can look through someone's health records and then give some diagnosis. Right? Now, if you look at health records, depending on how complex it is, the diagnosis may be easy or quick to give out. Right? So if I have two workers that are working, and I keep giving one person all the complex jobs, that means that that person will likely be using more higher CPU running through than the person who gets the much simpler work. Right? Or even if you are doing, let's say someone says, I'm going to be sending you some pictures to analyze, to search if you can do facial recognition. Some pictures, maybe if they are more blurry, may be harder to do the facial recognition for, meaning you're going to run more cycles to do it. So if I keep giving the same type of work to one and another category of work to the other, their work rates will be different. So when we talk about load balancing, it means that as much as possible, when you write your threads and they are working, you try and make sure that different jobs are split, or different categories of jobs are split around. Right? I hope you understand. Let's say I'm doing advising. Should we give all the first years to one lecturer, second years to one, third year to another, and fourth year to one? No, it will be difficult, right? Because the one doing for the fourth year, that means everybody who comes to him, he has to read through what? 4 years worth of class code or class history. Once the one doing first year, he'll be very happy. It's like, oh, have you taken any class? No. Awesome. What do you plan to take? Very quick conversation. So if you give everyone 30, 30, 30, 30, the person doing the first years may actually finish very quickly. Whilst the person who is maybe someone, the middle years are the difficult ones. The final year, usually people know what, well, it's all sorted out. But second, third year is the tricky part. So that person may spend a lot of time. Because the person will be asking, should I take this one? And then the third year I take. So that workload, that split, isn't very fair. Because the person doing the more complex task will spend more time. Same for CPUs and threads. If you make workers, and they are picking up work, and you give one person all the difficult work, that person, when he's running, will spend more cycles on it. Right? So as much as possible, usually we try and break off and sort of have different categories of threads or of work spread across. So we give everyone some first years, we give everyone some second years, we give everyone some third years, give everyone some fourth years. Right? Just to get some balance. I hope people are understanding. Right? Or even your courses. I think you realize that maybe you have not paid attention, but we don't give you maybe 4 CS courses in one semester. It's very rare. Usually they try and do some CS, some writing, some leadership. They won't do leadership like leadership 1 is possible, but I don't think it's encouraged. 1, 2, 3, 4 leadership all in 1 year or 1 semester. Do it. Some people will be very happy, some people will be very sad. The people who enjoy it will be very happy. Who don't, very sad. Or if it's programming, someone says, okay, I'm going to give you 4 courses that all do computer science, 1 semester. Some people will be very happy, some people will be very sad, just because different people think in different ways. So if every year we give everyone a mix, some CS, some BA, some leadership, some arts, then people can what? Even out. Someone will be at an extreme disadvantage. Let's say they don't like coding at all. They won't be in big trouble every semester. So you try and even things out as far as the jobs, so that different CPUs can work at more or less the same rate. Are people cool? Alright, so we talk about 2 types of parallelism, data parallelism and task parallelism. Right? So for data, it means that we can split the data. We don't have to necessarily worry about creating different types of processes, different types of threads. We'll just be, okay, I'm going to just duplicate the threads across and send the work. So video processing is a good example for data parallelism. The same video, I just break it into pieces. But the processor, that means the code that does the encoding, I just duplicate that code in different places. Right? So this is a very common one. I know you hear things like big data and so on. When you hear big data, one of the things they do, a lot of data parallelism. Just realizing that the data is a lot. If we have more processors, more CPUs, more memory, and just replicate whatever you are doing. So it says, okay, everyone is always calculating average. Therefore, let's have the average calculator on many, many, many machines, and then split the data and send it to different machines. So for data parallelism, the emphasis there is splitting the data, not really rewriting all the workers and threads and so on. It's not so much difficult that way. The other one, when someone says task parallelism, that one means that you're actually thinking of the different tasks that are happening. So if it's a web server, someone can say, okay, there's something that does processing of the form. There's something that does rendering the page. There's something that does maybe doing database access. Can we do these in parallel? Right? So that means for every type of task that you can come up with, can you do them in parallel? So some of the web servers, they do mail, they do database, they do different tasks. Can we do these in parallel? Database is a different task from someone who is doing mail, different task. So that's what we mean when we talk about task parallelism. So if you see that in the text, that's the difference. So comparison, data has to do with just duplicating the data, not duplicating, splitting the data, but you're going to be using the same processing on the different cores. Whilst for task parallelism, we are thinking of having different ways of doing slightly or different things that are being done, right? But then doing it on different cores, right? So if you have your phone, some things could be done in parallel, some things no. Maybe if you are doing, and I think some phones now have quad core, 8 core, it's a lot of cores running. Some of them maybe are saying, oh, okay, we can do better video, and what they will do is usually it's the same. If it's a video is rendering, they'll just say, this part of the screen goes to this core, this part of the screen to this core, third part to this core, fourth part. Right? That is a type of data parallelism. That means each core is doing the same work, but it's just the data that has been sent. But if we talk about task parallelism, someone would say, okay, I have a phone. The messaging is running on one, the email is running on another, uploading, downloading is running on another, my browser is running on another. So different tasks. So task parallelism, different tasks on different cores. All right, so this is, I'm going to move to code next. Right. So before the code, I'll talk about testing and debugging. I know people do most people use NetBeans or not? Okay, so I'll just use NetBeans as an example, but okay, I'll come back to this soon. Before you start coding, make sure that you actually have a plan. Trial and error isn't going to work for this type of approach. So that means that you have to sit down and plan out how things are going to work. That, okay, I'm going to have something start over here, connect over this port, something here receive on that port, process. So you have to write out detailed plans for how you're going to implement it. You cannot be doing the trial and error, okay, let me put an if here and see. Let me do an else here. So it's good if you plan it out. Okay, so OS class. When I was in school, OS class was the only time when I was forced to do a flowchart, because previously all classes I was not really. It wasn't challenging. We weren't thinking about multiple things. But when it got to OS and the threads started to come in, I had to sit down. So please don't be, what's the word? Don't feel too big. Don't be ashamed if you are forced to do a flowchart. Right? If you draw a flowchart, it's fine. You can say, okay, this process, I'm going to start. You do this task, you do this task, you do this task. Right. Now, if you do this, it will help you refine your thinking. For your group members, it will also help you debug certain things. Because without coding, you have to be able to have sound logic. It has to work logically. So please, if you are running into issues, don't just, I know some people say, oh, I wrote this if and it didn't work. I'm like, what is your plan for your code? Right. And in the previous one, I was seeing that as well. Some people, yes, they can code, but the thing is, you need to be able to know, no matter how complex the scenario, and this was a small piece of code with forks and so on, you have to be able to sit down and debug the code. That means before you debug though, you have to have a plan to know, my code is doing, it does this, it does this. You must have a plan. If you don't have a plan, you will spend a lot of time, and the reason why you started doing flowcharts was, testing was becoming difficult. Because without a flowchart, how can you even know what you are testing? But if you draw the flowchart, you can say, okay, I'm going to see if I can pass on this line. Here, 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 here. Second flowchart, can I take this branch and test this part? So we did a big flowchart. And when we were testing, then it was easy to do. Because then one said, okay, have you tested this branch? One says, okay, yeah, I've done that. Have you tested it? Okay, I've done this test. Then once you've done all the tests, you know. So even before you start putting things together, you've tested each component. Something is supposed to do addition. Did you pass in the value? What does it do? You pass the wrong value. Test the parts. Because with threading, things are running off doing their own work. And if it's not properly tested, you will start to see, oh, I don't know what's going on anymore. It's not working, and you don't know where it stopped working. Right. So those of you who are doing software engineering, even if you are not, review your flowcharts. They are also what we call sequence diagrams. If you don't know what a sequence diagram is, please, there are so many tutorials online for sequence diagrams. Check out sequence diagrams. Unlike the flowcharts, the sequence diagram will have different, I think we saw one sequence diagram, there was one in the chapter previously. They didn't. It was when we were talking about moving between 2 or 3 threads. The context switching. That was a sequence diagram. Oh, come on. Okay, we are very close. This one. So you see that this one, it's not really a flow chart because it's showing different things that are happening in parallel. With a flow chart, you don't always know if things are happening in parallel. Some, okay, you can do 2 branches, but for this one, it shows us like a call going around from one place. I do this, I go back. So this is showing a nice one. And of course, this is a state diagram showing you that from one state you can move to another. So as much as possible, you can utilize, like if someone asks you to implement this, if you had a diagram, it would be much easier to do than if you wrote it out in English. I don't know if people like the English long writing, but when you see a diagram, you go, okay, if I see this, I should change the value. If I see, this is much clearer. Right. So please, as much as possible, use diagrams, right? Test your code, right? And for testing, there are some people that when they are working in a project, they would say, oh, until the other person finishes everything. You don't have to wait till the other person finishes. If you are asked to write a function that does a certain task, put in some value. Call the function with some values and see. I hope you understand. If someone says, okay, someone else is doing a reading from the file, I am going to take the data from the file and process. Do you have to have the file before you start? No. You can make an array, put in some data, and what? Run it and see, oh, if I were to take the things from the array, put it to my function, what would be the output? Before the guy who comes with his file and says, oh, I've done the file IO, I can read from a file. So don't let the other person's, whatever they are doing, slow you down. Whatever task you are given, you can think of what functions do I need? What are my inputs? What are my outputs? Write it, test it, and make sure it's working. Before the other part comes, you slot it in. Right. So I'm going to give you a 5-minute break, and then when we come back, so that is at 9:30, currently it's 9:24, we are going to look at some code snippets in NetBeans. Right, so 5-minute break, relax, and then we'll come back and do, so 9:30, it's 12 minutes to 9:30.